One more to go. Thank you for sticking with it. Like I said last video, these first few units of the class tend to be longer lectures. You're getting a lot of background information, and then we start to kind of focus in on smaller and smaller topics. So hang in there. Metamorphic rocks. So we have igneous rocks, if we're looking at igneous rocks, volcanic activity or magmatic activity, that's what they tell us. Sedimentary rocks tells us weathering, erosion, tells us possibly depositional environments, it tells us oceans might have been in certain locations. And then we get into metamorphic rocks. These are my favorite to look at, my favorite to find. They're just weird. They're weird looking. I like them. I'm weird. So we're in now this realm of the rock cycle. So metamorphism, to morph means to change. So what we're doing is actually changing existing rock to something else. So that's the key of metamorphic rocks. We're changing sedimentary rocks, we're changing igneous rocks. Hell, we'll even change other metamorphic rocks. And just with heat and pressure, we can alter those rocks to something a little different. So again, metamorphic rocks result from some existing, what we call parent rock, undergoes heat and pressure without melting. If there was too much heat and pressure with the existing original parent rock, well then it would turn to magma or lava, and now we're back in the igneous realm. Right? But we're talking about just enough heat and pressure to kind of change things a little bit. And when we're talking about change things, I'm talking about the composition. We can get new minerals to start to grow. All right? If we have new minerals, that means a new rock. Texturally, the minerals can stay the same, but they can kind of alter and kind of move and align in certain directions. Or we can get both. So heat and pressure can cause both of these. What the heat does, it can increase the rate of a chemical reaction, so getting new minerals from the parent rock, thus changing what the rock is. Remember, rock is defined by usually two or more minerals. So if you're changing one of those minerals, therefore you're changing the rock. You're morphing the rock. So heat is one agent of metamorphism, and then pressure. Couple of different ways. You can get pressure kind of from above, from kind of overlying sediment or rock, and that usually forms kind of more denser and smaller minerals, or differential pressure, which is typically a higher pressure directionally, usually from plate interactions at boundaries, usually convergent boundaries, and it exerts a hell of a lot of force in kind of one direction. Hot hydrothermal fluid is also an important metamorphic agent as well. A little complex, but heat and pressure are pretty much the ones we want to focus on. So let's say we have some existing rock layers and we get some magma intrusion coming up. The heat radiating off of that magma will alter the parent rock around it, or sometimes called the country rock that the magma is intruding into. So heat can be an agent of metamorphism. Or just as you continue to pile sediment and rock layers above, that pressure pushing down can also create metamorphism. So heat and pressure is what we're looking at. Again, let's say you have a depositional environment. As you get more material being deposited, the pressure is increasing. So that can create metamorphic rocks. Here's another example of pressure. Looking at this convergent boundary, it looks like a continental to continental convergent boundary. You can see how things are deforming via heat and pressure. So hydrothermal activity, so water, hot water can also creep in and change things on a very small scale, but still kind of, I guess, somewhat related to heat. That can happen either in the crust or on the seafloor. But for the most part, just focus on heat and pressure. Right? Heat and pressure. Metamorphic rocks tell a story about heat and pressure. These rocks have undergone extreme heat and or pressure. All right. There's a few different types of metamorphism. Contact metamorphism is when there's existing rock and a magma intrusion kind of comes in, an igneous body, the heat from the magma is in contact with this other rock, which alters it. so metamorphose it, so then that rock changes, or hot fluids can induce that as well on a smaller scale. Both, whether it's a magma intrusion or hydrothermal fluid, you're really only altering the rock right around these intrusions. So contact metamorphism, that's usually done by heat. Regional metamorphism is the most common. This usually happens over large areas, tremendous pressure and temperature. This is kind of very common at convergent boundaries. So if we've got, slabs of tectonic plates colliding, metamorphism is going to happen over a very long range, and that's called regional metamorphism. A lot of heat, a lot of pressure there. Dynamic metamorphism, a little less, but kind of around fault zones where we get some differential pressure. Excuse me. And then burial metamorphism, again, occurs more sediment and layers build up, more heat and pressure below can start to alter things a little bit. But again, of those, regional metamorphism, by far the most common. Contact metamorphism, pretty common as well. Burial, and then dynamic, a little less common. So just to illustrate some of those, this looks like a convergent boundary between continental and oceanic crust. Looks like this stuff gets crumpled up, so that's regional metamorphism happening there. We have some magma kind of intrusion here, so whatever this is coming into contact with, we get some contact metamorphism. We have sediment building up, so down near the bottom where there's feeling the pressure of all the overlying sediment, we get some burial metamorphism happening as well. Some of the different, there's two different rock textures we can look at, and that can help us ascertain what type of metamorphism, therefore, what occurred in the past just by looking at the rock. Again, all of this is like looking at the rock and trying to begin to tell the story of what may have happened, at least at some point in the geologic past in a particular area. So the two types of metamorphic rock textures are foliated and non-foliated. So foliated are metamorphic rocks that have kind of lines or layers. Due to pressure, the minerals may be lined up, or how certain things were originally deposited and then eventually squished a little bit more together. You get these layers of material or lines of material, whether it's horizontal or vertical, it doesn't really matter. But due to pressure, things kind of start to line up. And you will see that in the rocks. You will see lines of minerals. You will see kind of layers in there as well. That's a foliated metamorphic rock. And if it doesn't have the lines and layers, then it's non-foliated. So there you go. Yeah, so you take some existing rock, the minerals are all arranged randomly, say in a piece of granite. You begin to squish it, and all those minerals kind of start to line up, and we can visually see that. We can see these lines and or layers of metamorphic rocks, and that's, again, foliated metamorphic rocks. So, for instance, this rock, it's a little blurry, I see, but it has a foliated texture. You can see the lines of minerals starting to kind of, get together. That's probably indicative of regional metamorphism. This is a non-foliated metamorphic rock. It has undergone metamorphism, but you don't really see the lining up of minerals. That's maybe a lower grade metamorphism, like contact metamorphism. A lot of heat, but maybe not a lot of pressure to get minerals to line up. Maybe here's a little bit better look. All right, again, you can really see the lines of minerals that kind of banded together. So foliated, non-foliated, there's no lines or no layers. Okay. So when we're looking at and trying to identify metamorphic rocks, that's the first thing. We kind of break it down from there. How those minerals are lined up can tell us how much metamorphism, how much heat and pressure. The more heat and pressure, more likely we're looking at maybe regional metamorphism over here. This might be more burial metamorphism, maybe low-grade regional metamorphism. Maybe we have some contact metamorphism going down here and these non-foliated ones. But metamorphic rocks depend on the parent rock. Whatever the original parent rock that underwent metamorphose was, that's what then would determine the metamorphic rock. For instance, if I take sedimentary rocks like shale or mudstone or siltstone and I apply some heat and pressure, I get the metamorphic rock slate. I take slate, metamorphic rock, and apply heat and pressure and I get phyllite. I take phyllite, apply a bit more heat and pressure, and I can get gneiss, so I take phyllite, apply heat and pressure, and I get schist. I take schist and or maybe other igneous rocks like granite, and I can get a metamorphic rock called gneiss. Gneiss, like naughty or nice, nice. The G is silent. If I have a limestone, which is a chemical sedimentary rock, and I apply some heat and pressure, I can get marble. Marble very commonly used in gravestones and like statues and things like that. If I apply heat and pressure to sandstone, which is a detrital sedimentary rock, I can get a metamorphic rock called quartzite. Quartzite, there's a city in Arizona called Quartzite. Can you guess why? Got a lot of quartzite around them parts. And then bituminous coal, which was a biochemical sedimentary rock we talked in the last video, you apply some additional heat and pressure to that and you get anthracite, anthracitic coal. It's still coal, but it's actually a little bit more compact, therefore a higher grade coal. So foliated, non-foliated, the rock name is based on the texture and the parent rock, so you can tell a whole hell of a lot from, you can tell what rock it originally was, and if you know originally what it was, then you can figure out that sort of environment, but then what sort of environment was necessary with heat and pressure to make the actual new metamorphic rock, how much metamorphism, was that burial, was that regional? So rocks tell a story. It's one thing to be able to name a rock. I'm actually less concerned that you can name an actual rock, more so that you can kind of look at it and you're like, oh, I think this is a metamorphic rock, and that means, you know, maybe there was some convergent boundary regional metamorphism. This looks like a vesicular igneous rock, so that means there was some sort of kind of explosive volcano in the area. I don't care necessarily all that much that you know the name of it, but that you can start to tell the story, because that's what historical geology is. We're trying to tell the story. All right. What's happening here? All right, so anyway, can you see this thing? I hope you can't see that. So we've completed the rock cycle. Again, we usually start the story with igneous rocks because remember, Earth started off as a molten ball of magma and lava. So cooling, the first rocks were igneous rocks. But in reality, you know, we don't have to start there. The rock cycle can go any which way. All right, any which way. But we just kind of, for the sake of the story, start with igneous rocks, then the sedimentary rocks, then the metamorphic rocks. But again, this path can go any which way. These rocks can go from one to the other, back and forth through time. Okay. Again, it's more so the story that these things tell you. You know, if you're looking at a igneous rock where you can pick out the different mineral grains, you can tell that this is some sort of magmatic or lava activity. If you're looking at layered sandstone, you can tell the story of deposition, burial, lithification, possibly, you know, oceans in this area. And if you're looking at, for instance, a foliated metamorphic rock, you can understand, oh, this is undergoing high heat, high pressure. Maybe there was a boundary in this area at one point. Nothing to do with the name of the rock, just by looking at the texture and what it's trying to tell you. That's hard to do, all right? We'll work on that a little bit in here. We'll work on that a little bit in the lab. By no means will you be an expert, but it's just, you know, getting the idea of how that kind of works. That brings us to the end. It's been fun. It's been my honor. Thank you for sticking through with this one. I know it was a long one. Until next time, I'll see ya.